Hello, welcome to physics. This is just a short lesson on interpreting force versus time plots, how they can give valuable information on the impulse an object or system underwent within a certain time frame, and through the impulse momentum theorem, how if we have starting mass and velocity, we can determine final velocity at the end of that time frame. Let's take some generic force versus time plot. In this particular case, the piecewise function allows for various well-known geometric shapes to describe the area of our force versus time plot. We have an object that experiences positive 20 newtons of force within the first 3 seconds, then dropping down to 0 instantly and slowly decreasing to negative 30 after 2 more seconds, or from 3 to 5, and then from 5 to 6 seconds, after it drops up to 0, it slowly increases to positive 10, stays at that value for 1 more second, and then from 7 to 8 slowly decreases to 0. Some sample problem, initially traveling at positive 3 meters per second, so that's the initial velocity. A 10 kilogram object experiences a net force over 8 seconds. As described above, that net force can change with time. That is the net force at each particular second. Describe the net impulse and final velocity after 8 seconds. Determine those values and assume, if necessary, that the gravitational constant is 10 meters per second. Well, what we have here is different shapes on our force versus time plot. In reality, if we were to treat this like calculus, the impulse is just the integral from some time range to some final time times the force function with respect to time. Now, oftentimes, what we'll see in physics labs is force usually is some constant over some period of time, which just simplifies the equation to impulse equals force multiplied by time. But more importantly, all this is to say is impulse is the area underneath a force versus time plot. So within this particular force versus time plot, we don't have some crazy function. We have 3 discrete regions of shapes. From 0 to 3 seconds, we have some rectangle describing our area of force versus time. From 3 to 5, we have a triangle describing negative area or negative impulse. And from 5 to 8 seconds, we could think of this as either 2 triangles and a square rectangle, or more quickly, we can just treat that region as a trapezoid. Each of these geometric shapes have well-defined formulas for their areas. For 0 to 3 seconds, the area is described by a rectangle. Therefore, impulse equals the length, positive 20 newtons, times the width, 3 seconds, or the width that spanned from 0 to 3 seconds. Therefore, the difference is 3. 20 newtons times 3 seconds equals positive 60 newton seconds. From 3 to 5 seconds, the area described by that region of time is in the shape of a triangle, so 1/2 base times height, or impulse in this region is 1/2 times the height of negative 30 newtons times the time range of 2 seconds, or it went from 3 to 5 seconds, so take the difference and get 2 seconds. 1/2 times 2 seconds is 1, so negative 30 newtons times 1 second is negative 30 newton seconds. Lastly, from the time region 5 seconds to 8 seconds, this is a trapezoid. We could break it up into triangles and quadrilaterals, like rectangles or squares, but let's just treat it with the trapezoid formula of 1/2 times height times the sum of base 1 plus base 2. Well, in this case, the impulse would be 1/2 multiplied by the maximum height of our trapezoid, which is positive 10 newtons, times the quantity of base 1, the top, which span 1 second or 6 to 7 seconds, and the bottom, which span 3 seconds or from 5 to 8 seconds. Therefore, that's 1/2 times positive 10 newtons times the quantity of 1 second plus 3 seconds, which gets us an impulse along that region of time of positive 20 newton seconds. All we did was look at the area at different discrete, well-defined regions in our force versus time plot. If this was a variable function and not a piecewise function, then you could just take the integral, but here we're looking at it algebraically and geometrically. Now, calculating the total impulse, essentially from 0 to 8 seconds, we add up our different chunks, positive 60, negative 30, positive 20. Those add up to positive 50 newton seconds. All right, that gives us the total impulse that 10 kilogram object experienced from 0 to 8 seconds. That's the net impulse. Now, the nice thing about the impulse momentum theorem, that says that the net impulse an object experiences over a certain time range is equivalent in magnitude to the change in momentum across that time range. Impulse is in units of newton seconds. Momentum is in units of kilograms meters per second. Newtons being kilograms meters per second squared times that additional second just cancels out to kilograms meters per second. Whenever you use impulse, it must be in newton seconds, but momentum is formally in kilograms meters per second. Now, the change in momentum, that's just the final mass times the final velocity minus the initial mass by the initial velocity. Usually we treat mass as a constant, so the change in momentum is just the mass times the change in velocity. Bringing that into our known values, with the change of momentum being mass times the quantity of final velocity minus initial velocity. If we rearrange that equation to solve for our final velocity, that's just the change in momentum divided by mass plus the initial velocity equals the final velocity. So in this particular case, the final velocity is positive 50 kilograms meters per second divided by 10 kilograms plus the initial velocity of positive 3 meters per second comes out to a final velocity of positive 8 meters per second. And that 50 kilogram meter per second came from the impulse momentum theorem, where J equaled positive 50 newton seconds. Therefore, that's equivalent to change in momentum equaling positive 50 kilograms meters per second. And that's just a generic example of how we can go from a force versus time plot, and starting with velocity and mass, initial velocity and mass, we can determine our final velocity. If we didn't know velocity or mass, we could still determine at the very least the net impulse across this sample force versus time plot. And this is just an example in physics where many times there's extra information that's not necessary, like how we did not actually need the gravitational constant in any way, shape, or form. In any case, that is just around the 9-minute mark. Thanks for watching, and peace.